Good afternoon, ladies and gentlemen. Let me introduce this 11th Accelerate webinar on carbon capture, utilization and storage. The specific topic of this webinar is novel approaches for CO2 conversion into valuable products. Let me spend just a couple of words about Excel, but the first recommendation is to switch off microphone and camera during the webinar just to avoid problems with the speakers, and all the questions can be write down in the question panel in the GoToWebinar platform, and the speaker will answer your questions. Just a couple of words about Excel, which is a network. It's basically Research Infrastructure Consortium based in Norway, France, Italy, UK, and the Netherlands, with 23 facility owners and more than 80 research facilities for advanced research on carbon capture, transport, utilization, and storage. And this webinar series is organized within the Accelerate project, which is an Horizon project which is going to be completed next month, with the main goal to improve the Excel research infrastructure and extend the activities towards transport and utilization of CO2, so from CCS to CCUS. And finally, this webinar is part of the Accelerate capacity building program, together with a series of initiatives to promote the capacity building within the Accelerate research infrastructure. So let me introduce the speakers today. Professor Manuel Alvarez Guerra from Universidad de Cantabria in Spain, and Robert de Kler, which is an energy expert at TNO in the Netherlands. So let me give the speech to Manuel.
Okay, so should I start sharing, I think? Okay, show my screen. Okay, so
okay.
So can you see my screen?
Yes.
Okay. So, well, thank you very much. First of all, I would like to thank the organizers, and especially Dr. Alberto Pettinau, for inviting me to give this talk on CO2 conversion by means of electrochemical processes. It is a pleasure to take part in this webinar. I have divided the presentation in these parts. First, I will start with a brief introduction on the problem of CO2, and then we will see some general ideas about the electrocatalytic conversion of CO2 to products, which is a very promising and attractive option to tackle this problem. And we will also see some examples of the influence of different factors on the performance of these electrochemical processes, particularly the crucial role that not just the nature of the catalyst, but also the properties can play. In the last part of the talk, to further illustrate this, we will quickly go through an overview of some results that we have obtained on the development of continuous electrochemical processes for obtaining format. And finally, I will finish with some concluding remarks. So if there is any moment in which you stop seeing my screen or listening to me, please let me know. So let's start with the introduction. Different strategies for reducing CO2 emissions and mitigating climate change are being considered, such as to increase the efficiency of energy use, reduce the reliance on carbon-based fuels, changing to renewable energy, or strategies to increase carbon sinks, where we can include the carbon capture and utilization, that is, to capture CO2 from flue gases of combustion to avoid the emission to the atmosphere, and then use this captured CO2 for a beneficial use or for converting it into useful products, closing in this way the cycle. It is important to be aware that in many industrial applications, it can be challenging to contemplate completely eliminating the use of hydrocarbons or raw materials that generate CO2. For example, in the production of electrical energy using fossil fuels, or in the cement and steel manufacturing industries, the use of hydrocarbons or raw materials with CO2 emissions is an intrinsic part of the process. In cases like this, for industries in which sectors decarbonization is challenging, carbon capture and utilization technologies appear as a promising opportunity to transform these challenges into sustainable solutions. Captured CO2 can be used in new processes or products, creating in that way additional sinks in the natural carbon cycle. So, CO2 capture and utilization can contribute to the transition to a more sustainable and low carbon industry. This schematic is taken from the Synergy initiative, which is a European network bringing together stakeholders in the production of synthetic fuels. And I find it interesting because it visually represents the degree of maturity of different CO2 valorization technologies. Darker colors represent more mature technologies with higher TRLs, while lighter yellow colors indicate lower TRLs. So on the one hand, in the right part of the figure, we can see that currently there are mature and affordable technologies for generating electricity from renewable sources, such as solar or wind. However, these technologies lack direct storage options. On the other hand, long-term storage is achieved through technologies based on the conversion of solar energy into biomass. First and second generation biofuels based on biomass are affordable, but they are not scalable to meet the global demand for fuels because due to their low conversion efficiency and consequently a significant impact on land use. In this way, a very interesting approach is to develop technologies that merge these two concepts in the middle of the scheme, here with yellow background, strategies that we could call artificial photosynthesis, technologies that mimicking nature directly convert CO2 with solar light into a final product of interest. However, the yields of this direct conversion are still very low, so in the shorter term, an option that has reached higher levels of development is the conversion of CO2 using renewable electricity. This is what we could call electrochemical valorization of CO2, which requires supplying electrical energy to establish a potential between two electrodes, a cathode and an anode. The electrochemical conversion of CO2 is a particularly attractive pathway because it has the great advantage of mild operating conditions. It can be performed at ambient temperatures and pressure. Of course, we need energy for these processes, and a key requirement is that the electricity used for CO2 conversion must be renewable or at least come from a carbon neutral source. In this sense, I think there will be great opportunities for these electrochemical processes coupled to renewable sources, because these processes can be an excellent way of storing energy from renewable sources that are intermittent, like wind or solar energy. The idea as a future option would be to use excess renewable electricity from intermittent sources that otherwise could be wasted to reduce CO2 to chemicals, to products, which could then be used as fuels in fuel cells or as raw materials or building blocks. Perhaps we can distinguish two electrochemical ways of using CO2. In a very general way, CO2 can be reduced directly to obtain different types of products, or CO2 can be used as a reactant in electrosynthesis. This means to find new routes to obtain chemicals with added values such as organic carbonates or carboxylic acid that involve the use of CO2 as one of the reactants. Both could be interesting options, but the most studied approaches are those that imply the direct reduction of CO2. And here we can see in the figure clearly the products that have attracted the greatest research efforts so far. Carbon monoxide and formic acid, or formate, which involve the reduction of CO2 with 2 electrons, to methanol, which implies 6 electrons, and to hydrocarbons like ethylene or methane that need 8 or 12 electrons. So the most studied way of electrochemical valorization of CO2 is the direct electroreduction of CO2 in the cathode, 2 different products that are reduced forms of CO2 as we have seen. We'll focus then on direct electroreduction of CO2. And when we look at the equilibrium potentials of these different CO2 reduction reactions, we find that these potentials are usually in the same range of hydrogen evolution reaction from water, which acts therefore as a competing reaction with CO2 reduction. And in fact, another issue is that CO2 reduction does not occur in reality until a much more negative potential is applied. So one of the aims in the research on this type of processes is to lower this open potential as much as possible to increase the energy efficiency. Research on the direct electrochemical reduction of CO2 has shown that different products can be obtained and many factors can have an influence on the performance of these processes. In this sense, it is important to mention that to assess the performance of approaches for the electroreduction of CO2, there are several figures of merit that should be considered, including current density, the Faraday efficiency, which is in fact a yield at the percentage of the charge supply that is used for obtaining a certain product, and other metrics like the energy efficiency, the rate of production, or the concentration of products obtained in liquid phase. As we'll see later, the great challenge is to optimize all these figures of merit at the same time. So the yield and the type of products that we can obtain from CO2 electroreduction depend on many different factors. The conditions of temperature and pressure, as well as the reaction medium, have an impact, of course, but most electrochemical CO2 conversion approaches have focused on ambient conditions and aqueous medium. The nature of the electrode material is crucial. These catalytic materials have mainly been metals. However, we will now see that even with the same material, with the same metal, depending on its properties and the electrode configuration in which it is used, the products we obtain can vary significantly. This is a qualitative reaction scheme of the CO2 conversion to show that the role of the catalyst is to lower the energy of the intermediate. So, as I said, the nature of the material used as catalyst has a strong effect on the main products obtained. For example, in aqueous media at ambient conditions, copper electrodes mainly yield mixtures of hydrocarbons and alcohols. Carbon monoxide, CO, is the main product at metal electrodes like gold, silver, or zinc. And other metals, such as lead or tin, are selected for the production of formic acid and formate. So, of course, the type of catalyst is very important, but not just the nature of the catalyst. There are also other properties that can have a dramatic effect on the performance of this CO2 electroreduction. Now, let me quickly show you a few examples. First, the size of the catalytic particles has an important effect. For example, this is a relevant study which proves that there is an exceptional dependence on the activity on the size of gold nanoparticles for CO2 electroreduction to carbon monoxide, or in another highly cited paper from the same group of Professor Rodin and Strasser, in this case with copper nanoparticles, where depending on the size, the selectivity can change from CO and hydrogen to methane. The morphology, the shape of the particle, also has an effect on the performance. This is a nice example of the passive dependent selectivity of copper nanoparticles. So cube-like shape gave more ethylene. With hexarhombic dodecahedron-like copper nanoparticles, the selectivity changed to methanol, while octahedron-like shaped copper mainly converted CO2 into CO and methane. Or this other example, depending on the shape of the copper nanoparticles, spheres, cubes, or octahedra, the efficiencies, the selectivities to methane and ethylene change significantly. The oxidation states of the particles can also be very important. For example, in this relevant paper, in JACS from researchers of Stanford University, oxide-derived gold nanoparticles were much more selective for the CO2 electroreduction to CO than polycrystalline gold electrode. More recently, with this study with the copper nanoparticles with PVP capping, the results show that surface oxidation of copper species plays a crucial role in the electroreduction of CO2, turning selectivity to methane or multi-carbon products with more than 2 carbons. So finally, another example on oxidation states can be this study from my colleagues in our department in the University of Cantabria, in collaboration with the University of Alicante, which found that the use of oxides of copper and zinc nanoparticles gave higher selectivity to metal. Heteroautodoping is a strategy that is receiving increasing attention to improve the catalyst. The doping can be with no metal atoms, such as in this example, in which carbon doped with sulfur and nitrogen promotes the CO2 reduction to carbon monoxide and methane. Or the doping can be with metal atoms, for example, nickel and graphene to give carbon monoxide with high and stable activity performance. Or another recent example, nickel nanoparticles in nitrogen doped with carbon, which also shows the good stability of this type of structure. To finish this part, the use of alloys can also show better reactivity and selectivity than their respective elements. For example, in this approach, bimetallic copper palladium particles give interesting parallel efficiencies to hydrocarbons. Or finally, carbon supporting nanoparticles of alloys, platinum zinc, gave high selectivity to metal. Everything okay? Can you hear me? Can you see me?
Yes.
Okay.
Yes, Manuel.
Thank you. So now, moving on to the last part of the presentation, we will quickly go through some results that we have obtained in the DIPRO research group in the Department of Chemical and Biomolecular Engineering of Universidad Cantabria on the development of continuous electrochemical processes for obtaining formate. Among the different products with value added that can be obtained from CO2 electroreduction, formic acid or formate, depending on its value, are considered some of the most attractive because apart from the traditional uses, formic acid and formate are attracting attention as fuels for fuel cells, as well as one of the most promising materials for hydrogen storage. This interest is reflected in a large and rapidly increasing number of studies focused on CO2 electroreduction to formic acid and formate. And in recent years, there have been important advances, but still research efforts are needed because several requirements, as we will see, have to be achieved simultaneously for a practical implementation. So we will quickly go through some of the main results we have obtained, and I hope they can serve as an example to show that improvement can be achieved, of course, depending on the nature of the catalyst, but also the electrode and the reactor configuration have a deep effect on the performance of these processes. Here we can see the common characteristics of the experimental systems that we have used in our research. We have always focused on continuous processes with ambient conditions of temperature and pressure, in which the core is the filter press electrochemical cell, in which the cathodic and anodic compartments are divided by an active membrane. The anode, is a DSA for oxygen evolution, and the cathode has been an electrode of different nature and configurations as illustrated in the slide. So now I will summarize some results of our research, starting with how the performance of the process has improved by the evolution of the configuration of tin-based electrodes. Then we'll briefly see how the use of bismuth electrodes have allowed achieving very good results. And finally, I would like to show you some promising results we have obtained by improving the process with changes in the reactor configuration. The first electrode configuration we tested was simply a plate, a lead plate or a tin plate. And we found in the results that tin gave better performance than lead. So we focused on tin as electrocatalyst. But in the next study, instead of a plate, we modified the electrode configuration to use tin particulate electrodes. And as we can see in the diagram, in this case, apart from the liquid catholyte, we also have another input stream of CO₂ gas. The particulate electrodes were prepared first with commercial particles of 150 micra and also of 150 nanometers to study the influence of the size, of the particle size. And we observed that the maximum rate of formate production was several times higher using electrodes of lower particle size, keeping similar Faraday efficiencies of around 70%, but also allowing operation at much higher current density. But remember that the results were obtained with commercial particles. So we expected that further improvement could be possible with tin particles of lower size. So in collaboration with the Institute of Electrochemistry of the University of Alicante in Spain, tin carbon supporting nanoparticles of much lower size, 10, 15 nanometers, were synthesized, and they were used for preparing gas diffusion electrodes, GDEs, which are formed by a carbon support, like toral paper, a microporous layer, and a layer with the catalytic particles, which is a configuration that enhances the three-phase boundary of gas, liquid, solid catalyst, and therefore reduces mass transfer limitation. In fact, the GDEs with the synthesized tin nanoparticles gave much better performance than the previous electrode, allowing to work at much higher current densities of up to 200 milliamperes per square centimeter, keeping good Faraday efficiencies, and particularly obtaining much higher formate concentration. With the aim of further increasing the concentration of product and improving the energy efficiency of the process, the next step was to study the operation with only gaseous phase in the cathode, avoiding the use of a liquid catholyte, so that the inputs to the cathode were just CO₂ and water vapor. For this gaseous phase operation in the cathode, we use the electrode configuration that we call CCMEs, catalyst coated membrane electrode. That consists of a graphene membrane over which we directly deposit the catalytic layer in such a way that the membrane acts not just as a separator of anodic and cathodic compartments, but also as solid electrolyte. The use of CCMEs improve the performance of the process, achieving higher formate concentration with similar Faraday efficiencies, and especially with the great advantage of lowering the energy consumption by more than half compared with the gas diffusion electrodes. Let's move on to the result with bismuth as electrocatalyst. A few years ago, there were some studies that pointed to bismuth as a promising catalyst for CO₂ electrode reduction to formate because it required lower overall potential than other. But at that time, there were no studies of bismuth electrodes in a continuous mode. So we decided to test the performance of carbon-supported bismuth nanoparticles of around 9 nanometers, again synthesized in collaboration with the University of Alicante, and we tested them both in the configuration of gas diffusion electrodes in order to test the performance at high current densities, and also in the configuration of catalyst-coated membrane electrodes, working in gaseous phase without liquid cathode. The results with the bismuth GDEs gave excellent values of Faraday efficiencies to formate more than 90% and 90 milliamperes per square centimeter. That only decreased to around 80% Faraday efficiency when the current density was increased. And lowering the catholyte flow, it was possible to obtain concentrations of up to 18 grams per liter. Regarding the bismuth CCMEs, we studied the influence of relevant variables and found that particularly the amount of water flow in the input stream to the reactor had a great influence on the performance. So there was an optimal value of input water flow, which gave a concentration of 26 grams per liter with the lowest energy consumption. And to end with the evolution of the results, let me quickly show you a work where we study the influence of the reactor configuration. Using a membrane electrode assembly formed by an aphium membrane, a current collector, and a gas diffusion electrode prepared with bismuth nanoparticles, and using as input to the cathode of the reactor only a humidified CO₂ stream. Well, with this configuration, we were able to, it was possible to get a better and direct contact of the membrane and the working electrode in the reactor, which improved the performance, achieving very high concentrations of more than 340 grams per liter, with excellent Faraday efficiencies of almost 90% and low energy consumption, which are remarkable results and represent one of the best trade-offs among the figures of merit reported in the literature. In this regard, from a technological perspective, formic acid along with carbon monoxide is the product that is closest to a potential commercial production through the direct electroreduction of CO₂. A study that we have just published in ACS Energy Letters shows that, especially in recent years, significant progress has been made in the continuous electroreduction of CO₂ to formic acid, with promising results for practical implementation. But currently, these processes can be considered to be at TRL levels 4, 5. In other words, excellent results have been achieved in some figures of merit, but it is necessary to continue research efforts to achieve the simultaneous optimization of all the different figures of merit. For example, not just achieving high efficiency, but also combining that high efficiency with a high production rate, a high product concentration, and low energy penalty. And of course, it is also necessary to explore the scalability of these processes for their implementation at an industrial scale. So, to conclude, let me remark that the CO₂ conversion by means of electrochemical processes is a promising alternative that is attracting increasingly, because it can serve to obtain fuels and products and microemissions, and it can also be a future excellent way of chemically storing electricity from intermittent renewable sources. In recent years, this growing interest has resulted in an increasing number of studies with significant advances in the electroreduction of CO₂ to valuable products, especially carbon monoxide and formic acid or formate. And our studies and those in the literature show that not only the type of catalyst used plays a fundamental role, but also its properties, electrode configuration, or the reactor setup. These results also suggest that the electrochemical processes for CO₂ conversion will have great future potential. But the majority of them is still far from reaching the requirements for commercialization. There are still many challenges to overcome, such as to continue improving simultaneously all the figures of merit required. Another aspect that will have to be assessed is the durability and stability of electrode, which has been hardly studied yet. And for example, the anodic reaction also deserves attention because the oxygen evolution reaction requires high energy, and there are opportunities for improvement there. So, great research efforts are needed, for example, of course, studying new electrocatalytic materials, but also optimizing electrode and reactor configuration, because as we've seen, they can have an important influence. I would like to thank the Spanish Ministry of Science for the financial support for different projects. And finally, this is a nice picture of the whole DPRO research group in the Department of Chemical and Biomolecular Engineering in the University. Thank you very much for your attention.
So thank you, Manuel. All the questions can be related to the end of this webinar. So let me give the virtual floor to Robert de Kler from TNO, the Netherlands. Please, Robert.
I don't think I do it right now.
Now, Robert, you have to select the other as you did before.
So, okay.
No, we see the not the yes, right.
It's okay
That's
now?
working.
Yes, that's fine.
Oh, thank you. Well, I will, my presentation will be about the ECCSEL and how we evaluate the carbon capture utilization technologies and how we want to bring them into perspective, the ECCSEL, let's say, services for the research institutions and industry. And for that, we have then an assessment, which was part of the Accelerate project already mentioned by earlier. So, so first of all, Accelerate has a focus or look into the direction of utilization of CO2. And for that, we did some assessments on what does this mean in terms of how it can contribute in CO2 reduction on the short term and the long term, and if there is some synergies in terms of research infrastructure. In my presentation, I'll mainly focus on the let's say how it can contribute in the reduction of greenhouse gases in terms of CO2 emissions. And that was mainly the result of deliverable 1.3. You can find them also in the ECCSEL, let's say, website, and then there's a comprehensive report on this topic. I only present the highlights and give my personal opinions or observations as a remark on top of it. So first of all, already presented, but it is if you talk about utilization, it is about a circular, it's more a cycle where energy from renewables has a crucial role. And I think at the end we want to reduce CO2 emissions into the environment, and whether it is from a direct source or from or via air capture, the technology itself doesn't change. So, but maybe a point source can be more effective than direct air capture. But on the longer term, we need to place maybe the capture technology at the location where also renewable is available, since this also involves a lot of energy. And then you can imagine that if you capture the CO2 based on air capture or sea capture technologies, you also need the conversion into a transportable molecule. And one molecule heavily have been elaborated already is formic acid, and then produced in an electrochemical cell as formate. Since formic acid is and just like water, it goes into the via the membrane to the other side of the anode, so you don't get a very selective product. That's also one of the challenges anyway in the electrochemistry of CO2 reduction, and also CO2 can cross over to the anode side, which is also not a nice and have all kinds of side effects. You will see that when you scale up technology, so you can do it at a very small scale, but as you go and scale up, so my personal observation is that you get a lot of issues with these type of things, which you don't see in a very nice lab setup. But the crossovers are very painful things which can hamper current efficiency and current density, of course, as well, and product quality. But this is the cycle where we're talking about utilization. So we look at CO2, which needs to be reused more or less, and crucial is the availability of renewables. We're looking more from how do you can select a technology, or how do you want to support this? When it also has to contribute on a reduction of CO2 emissions, but it also has should have an attractive economic value. Although the future value change, we don't know. We don't know what will be the future of but if we take out fossil-based products, then the prices of products will increase. But that and we see it already when we have this new legislation on import of products, but needs to be with a low CO2 footprint. You cannot see an increase of products. So most likely the economic benefits is always with a reference case against other solutions which has the same intention to reduce CO2. So that is important to know, because if you evaluate it against natural gas or crude oil, yeah, they win always, because we don't. That is really very simple. You pump it up from the ground and you can use it already, because you have the right energy, you have the right let's say conditions to make products, and the infrastructure is already there. Here we have other things. We need to have an infrastructure, maybe new emerging technologies, new products like formic acid or formate or acid, all kind of new things what happens here. Methanol, also more crucial element for this CO2 let's say value chain. And of course the topics in this picture shows that it has to provide some let's say indication that it really supports reduction of CO2 emissions and have a positive mitigation potential. So we did this assessment basically focusing on all those points, and I already mentioned CO2 can be used but also stored. So someone says, okay, if you have done a lot of efforts to capture CO2 and you make a fuel out of it, all the effort you did is wasted, because the fuel will be burnt in a car or whatever, or and it then goes directly into the atmosphere again. So that is the discussion what has been going on for years. But I think if we look at it, you can maybe store permanent CO2 in concrete, for instance, and that's why and other kind of products like novel cement, carbon fiber, which has a longer lifetime than the fuels, for instance. So that could be seen as permanent storage. And then there are direct use cases of CO2, but that is more or less as a medium solvent, or a medium for chillers, heat pumps, and you name it. And of course, you can use it for enhanced oil recovery, which is heavily looked at now in the States, where they have very nice incentives to do so. But we mainly looking at the conversion into products. And here in this scheme, there's a distinguish between energy storage and feedstock. I think it is subject to the final product application. For instance, some of those, like especially formic acid, can perfectly use for feedstock as a feedstock for producing fatty acids in a fermentation process, which has been proven to be that it can work on formic acid, and that those creatures can grow on formic acid and make a biomass culture, which can be translated later on into lipids, and lipids can be produced as a feedstock for sustainable aviation fuel. So an alternative for that. So there are processes. So here it is really focusing on energy storage or feedstock. But sometimes you can say, okay, but some products like methanol, DME, formic acid, they also can be as a feedstock again for another product. But okay, and especially you have this thermochemical, hydrogenation, electrochemical. There are also differences in there. The low temperature electrochemical process, the high temperature. I will say something about that a little bit, but not that much. And gas fermentation, and as I already mentioned, you have also this now liquid fermentation based on formic acid, which has a very promising place now in this value chain. So more about the CCU pathways, mainly thermocatalytic. The reverse water gas shift reaction with CO₂ is a very prominent one. I think it is still a challenge to get something at a commercial level. Then also you have the direct reduction of dry reforming, which may be also some promising technology where you can go from carbon monoxide and hydrogen back to existing value chains, the Fischer-Tropsch synthesis, and you make hydrocarbons. But you can also imagine that you can make olefins and go to a different route. There you go from olefins to an MTO plant. And from MTO you can go also to jet fuel. So there are significant amount of directions you can think of when you consider CO₂ as your starting point. But yeah, it all requires energy in. Reverse water gas shifts is an endothermal reaction, so you need to have somewhere an energy source. And in this case, you need heat, and you can maybe make heat from electricity, or you have to use some part of the heat which comes along with this value chain to make this reaction happening with steam or whatever. But that is the case. So you need to have energy in, and subject to the I think the energy required is also subject to the molecule you think of. As you see in the first raw, that is the formic acid, the formite, and the carbolic acids. They don't need that much energy. So they need energy, but as you see, they have the lowest requirements on energy. So you see this as well in your economics. If you have, for instance, formic acid has a certain value based on tonnage, not on heating value, then there might be already on the short term a business case. But formic acid is not a large market. I think it is only 700 kilotons a year total market in the world, maybe up to 1 megaton, but that's it. So you can get the full potential of this technology if you only make formic acid. So you need some other product, and the formic acid needs to be priced at a certain way that you also can make other products out of it. So it's important to understand that energy requirement is low to make formic acid, but then the next step, the energy requirements might be different. So if you have a fermentation process behind formic acid, which doesn't need that much energy, but require maybe a lot of formic acid, that could be in direction of large-scale deployment of CO₂ reduction and produce, let's say, feedstock for aviation fuel. So that could be a direction of electrochemistry based on formate and from formate to formic acid. And so I can go along those value chains, but what you see is, for instance, methanol, which needs much more energy. It has also higher heating value. And at the moment, biomethanol is one of the interesting ones because the mobility, shipping, and maybe also traffic is looking into methanol. But competition with ammonia is there because ammonia is a good alternative for the almost the same heating value. Okay, methanol is slightly higher, but the ammonia, it can be in competition with methanol for the, especially for transportation applications as a fuel. So you see this path, and important is to consider the energy value, the energy required to make the product. Another one also mentioned already, current efficiency. I'm happy that that is already explained. There's not, I think Faraday efficiency is something like how selective is the product you can make. And for instance, formate, again, you can, and carbon monoxide can be produced at a very high current efficiency, Faraday efficiency. Other product like ethylene, ethanol has a much lower Faraday efficiency, meaning you make a quite complex composition of all kinds of molecules where you also find ethylene in there. So you need to separate ethylene then from the product. in which with formate, for instance, you might make hydrogen and you make formate, or and then hydrogen is easily separated because it's gaseous and formate is in the liquid phase. So you can easily separate them, or at least you have the opportunity to do downstream processing, which is much easier than if you have a soup of molecules, which you also get. So efficiency, current efficiency is important when you go into this value chain and evaluate technologies. And you can see it also here. Then if you combine them, so if you have this energy requirement and you have the, let's say, efficiency of how you, at what level you can make a product. This is a recent study done by TNO to look at state-of-art perspective on electrochemistry. So they look at low temperature electrochemistry, the high temperature, so that's more or less the oxide technology, and a combination of it. And as you see, carbon and formic acid or formate, which can be produced at quite high current efficiencies, can also be potentially attractive into the market. So produced at a very attractive level. If you see the high temperature processes might be performing better based on this analysis. So very interesting, but still, if you compare then the value of the product and the price you actually make, and as you can see that with the gray bar, so there's still a potential gap, but the gaps may be 3 times the price you currently pay for it. But if in the future we can't rely on fossil-based products, then this 3 times or 4 times or 5 times, that is then relevant to consider. Not so the current price of formic acid is maybe not the relevant one, but the price between the different technologies, that could be more of interest. So, and then formic acid produced at a very high current density or at a very high Faraday efficiency, that makes the difference. And also already mentioned, to improve your system, you need to optimize all of those parameters, because if you want to minimize capex, you might consider using non-PMG materials. So go for nickel-based anodes and use a very simple tin-based cathode. Which is not, and then the only more, let's say, noble part in the whole, let's say, setup is then your membrane, which could be Navion membrane or bipolar membrane based on the functionality of your cell. But there you can see potential improvements of this technology. But at the moment, the levelized cost of these technologies, if you look at this table, is still higher than the actual price based on fossil fuels. I don't know whether they took in considerations, for instance, for formic acid, there's a huge CO2 footprint, so that's 2.7 or something like that. And that is, if you times the current price of CO2, most likely it will be at par. So then I think you can maybe already show a better result on the longer term when CO2 prices go up to 150 to 200 euros per ton of CO2. Then for sure these technologies will be more attractive, becoming more attractive. And one thing we also had to look at ECCSEL is the time of sequestration. How long is it out of the environment and does it come back? I think you can also consider, if you take something out of the ground, you have to put it back. And utilization should focus on the, let's say, on the cycle of CO2. So it maybe connects more to direct air capture or that kind of, or bio-based technologies. But of course, as a fact, if you make a sustainable aviation fuel based on electrochemistry, you took out some part of fuels which normally was produced based on fossil. So you have a contribution, but should not be the case that the contribution you have with production of SAF based on electrochemistry at the end introduced much more CO2 emissions because of the whole process steps in between. And we use electricity based on fossil fuels or something like that. So you have always to do a proper LCA analysis on this. But of course, the technology we are developing should be can give us a pathway towards renewables, and electrochemistry is one of that. But I can imagine also thermal catalysis can also provide this, or a combination of that. But the permanent storage and the fuels will be just going directly into the air, but doesn't necessarily say it doesn't contribute. Yeah, already mentioned potential of CO₂ offtake, or how we can convert. So if we go into the concrete, so there we see a very strong large amount of CO₂ which can be potentially stored permanently. We see a big market for fuels, and maybe the market will be larger than maybe this picture, but this picture is from 2016. If I have to make it now, then I maybe it will be slightly switch a little bit, but and then maybe fuels, methanol are for me a little bit subject to the application, but that more or less is in the same ballpark. But as you see, the fuels also have a high potential of offtake of CO₂, which is relevant because we want to reduce CO₂ at a larger scale and not on very low levels. So you need to look into the market and where are the value, where do you get the highest value for your CO₂? And at the moment, we think I think that is the sustainable aviation fuel market, because there's not that much alternatives. So if you can produce sustainable aviation fuel based on CO₂ and then or methanol based on via the CO₂ route, then there's a potential for large offtake and a nice market, because then the competing technology is the one which is also and it is strongly also regulated. So that you need to do something, and we don't have enough fatty acids, so there needs something like an alternative, and it can be via CO₂, via methanol, biomethanol, and then maybe on the long term CO₂ produced from methanol produced from CO₂. I think that is also interesting direction. Another thing what need to be considered is the maturity of the technology, as already mentioned, electrochemistry, whatever you think of, but formic acid is somewhere in between technology level 5 to 6. There might be some demonstration projects going on or starting, but that is waiting, and then you see the impact of CO₂ from an industrial source and how it will have impact on the electrochemical cell. And meanwhile, also upscaling of this type of technology has a lot of challenges, to be honest, and it's not that easy. So this all the green stars mainly focus on chemicals, and I told already that maybe some of them also can be used as a feedstock for fuels. And but we see a strong maturity in the early adaptation of CO₂ reduction is maybe using it for curing concrete and for building applications, because that can be on large scale. So we think that we should support this as ECCSEL these technology developments. And meanwhile, we're also focusing on the let's say the electrochemistry ones, because that is fed by renewables. Then it is an interesting one. And often you can see this combination with CO₂ capture. So you can think about direct regeneration of your, let's say, your solvent or into a product. So you go directly from an amine or a KOH solution into another molecule. That are the directions which you also could consider. And also here you can see also in the processes, you see also fermentation. They call it gas fermentation, but I think fermentation in general, aerobic fermentation process. I think that is it's going now quickly with these technologies. And let's see where we go. but we will certainly follow support electrochemistry and especially the combination with capture technologies. So I just want to make some conclusive remarks. As ECCSEL has adopted utilization as part of extension of the scope on research infrastructure. We also have now selected some technology developments, although we still not have we don't want to precisely describe priorities in this field, because we see a lot of technologies, a lot of developments, but we for certainly will support thermochemical conversion and usination processes. Electrochemical and photochemical conversion, high temperature or low temperature, high pressure, low pressure, it's all there. So subject to how it can contribute to the reduction of greenhouse gases. And for the short term, we think that solid carbonates can have a very good contribution on the short term. So we really follow those and support those directions. We not specify any priorities now yet for research, which we could do for storage and transport and capture technologies, but not really for utilization because of the complexity of the technology developments. We don't know actually what is the latest status, and there's a lot of developments going on, so we better be open-minded and keep it open, and until we know a little bit better where let's say challenges are coming to the surface, where we really have to focus on as ECCSEL, where we can support and get and support with services and infrastructure. I think what the good thing about our assessment is that we did a very good, let's say, first assessment. I think it was part of already other projects which already did an assessment, so we had the benefit to use those ones. They are also referred in this paper or in this presentation, but also in our deliverable. But it gives us a good indication which ones we should support, and where really we could in future could have an advantage as Europe, but also as a contribution to reducing greenhouse gas emissions, especially CO₂ emissions. And we see, of course, that I already mentioned that on the long term, CCUS is an alternative for fossil fuel, but if we still have fossil fuels in our mix, and that will not change that much in the near future. So we need to find products which has an added value, and there are no alternative for it, and potentially you can benefit from a business case, or industry might benefit from a business case, and we should also support those ones if it contributes to the reduction of CO₂ greenhouse gases. I think thank you for your attention, and that was my end for my presentation.
So thank you, Robert. Thanks again, Manuel. We still have a few minutes for questions, so let me invite the participant to type question in the question tab. I think in the far right part of the screen. So I don't see questions at the moment, but I have a question for both of you. In the second last slide presented by Robert, the electrochemical processes was located near the, I can say, in a between pilot and demo scale in terms of TRL, in terms of technology readiness level. Basically, what's still missing for the commercial development of these technologies?
Shall I answer? I can try to answer this. I think what is still missing, I think next to Manuel's research, but what he is doing is very good and very supportive for the development. I'm looking from an, let's say, more or less an, we need still better materials, cheaper materials, upscaling, and that's only a technology, you know. It's not about finance or whatever, just the technology part. We need to get, yeah, first transport layers, so we make sure that we have a highway of ions in the system, that kind. So we minimize unnecessary losses, and we are still not there because so much we need to know and grab our work together. I think it's important, share information with each other to really mature the technology. That's crucial because and I think very good. What I see is we mentioned formate, because if you, and some concepts have formic acid, actually direct formic acid production, but my lesson is to go for formate because I couldn't keep formic acid in one compartment. I lost it everywhere. So and I think a stable material, gas diffusion electrodes, maybe can still improve not particle. I thought very interesting presentation of Manuel about the size, of the structures and the catalyst and the shape of it. Very interesting. To know more about it, we need much more effort in research and infrastructure to get better understanding of this. We can do upscaling, but if you now go for a demonstration unit, your current density of a 60 cell unit with let's say production rate of 4 tons per day will not be high, will be 50 milliamps per square centimeter. But your current efficiency might be at a 90, so that is feasible. But that is the status where we are. And we want to go to 200 at large scale. So we need to go with a lot of things. And but I think Manuel can also add in here. But I think that is what I think about upscaling.
Manuel, you are probably muted.
Yes, sorry. I agree that we of course need better catalysts. I mean, we have to improve all these aspects that Robert mentioned, of course. I would add that I mean, apart from achieving all these metrics at the same time simultaneously, which is actually the challenge. I mean, to keep very high parametric efficiency, but a high current density with high concentrations of products, high rates. I mean, all this at the same time simultaneously. But also, I think we need to explore, which is something that is not still studied, the durability and the stability of the catalyst. I mean, there are studies in the order of tens of hours, hundreds of hours, but I think from a techno-economic analysis that thousands of hours would be necessary. So, I mean, there is a lot of research efforts there, of course, in the stability and the durability of the electrodes. And also, we need to bridge the gap between the laboratory conditions, that is studies conducted with just the pure CO streams. We need to bridge the gap between that conditions, ideal conditions, with the real industrial environment, where probably we will find CO2 streams with impurities from combustion processes, and this is something that will need to be studied as well, the influence of these impurities.
Thank you, both of you. Sorry. So I don't see other question in the in the box, so we can conclude the webinar. Let me thank again the speakers, and Manuel and Robert. Many thanks to OGS colleagues for organizing and leading the capacity building program within Accelerate project. And the registration of the event will be available online soon. So thank you very much again.
Thank you.
Thank you.
Alberto, I would like to Can you hear me?
Yeah.
Yep.
Yeah, I just would like to mention that the recording of the webinar will be available on ECCSEL YouTube channel. Thank you. Thank you, everybody.
Thank you.
Thank you.
Bye.